So what I'm going to do today is tell you about our NSF project relating to trying to improve our understanding of the Earth's atmosphere and the representation of climate change, and what this can mean to humanity. In a study that I'm doing jointly with scientists from NCAR, National Center for Atmospheric Research in Boulder, which is an NSF facility, and with the University of Maryland. And so I'm just going to get started and try to explain what we're trying to do. Well, first of all, global climate change is one of the most important issues facing humanity in this century. I'm not the only one saying that. Many, many people are saying that. Sir David King of the UK, who has been a science advisor for two different prime ministers in the UK, has gone even further to say that that not only is this one of the most important issues, it's perhaps the most important issue of all time, and certainly to him much more important than all our many concerns about terrorism around the world. Our Pacific project here is aimed at using blue waters to address key uncertainties in the numerical modeling of climate change, both in terms of what's occurring now and looking over the projections into the future and what that can mean to us. So we're doing that through using very high resolution global and regional climate models that allow us then to get a better understanding of what's happening at the very local scale in ways that we could not do before, in ways we could not do without something like blue waters. And we're also doing a number of sensitivity analysis to then look at improving the understanding of Pacific climate processes and interactions, and I'll say more about those later. But one of the aspects of it that's unique in using blue waters is that we use a new dynamical core in the model, which then allows us to use blue waters effectively. And it did take a lot of time to tune and test that new approach. Along the way, when we moved to blue waters, we also found that the global climate model at very high resolution with the new dynamical core also had a number of issues with treating convection that needed to be resolved. And so we've been a little slow in getting a lot going with this project, but we're now getting a lot of wonderful results, and those are going to increase dramatically over the coming months. One thing I will be talking about is time slice runs for 1979 to 2010, and then for 2070 to 2100 at a 1/4 degree resolution. And what that has enabled us to do is to look at certain aspects of severe weather in ways that could not be done before. And specifically today I'm going to talk about hurricanes, tropical storms. We're also doing analyses at a 1/4 degree run to go all the way from 1850 up to present, and then from present up to 2100. And those analyses are still ongoing, and so I won't be able to show you results in them. On top of that, we're running a regional model called WRF, the Weather Research and Forecasting Model, also developed by NCAR at very high resolution. We're running at 12-kilometer resolution with that. It's about 1/8 of a degree. And that's enabled us to look at climate changes over the US in ways that are quite unique. And I'll talk more about that. And then finally, we're doing a series of sensitivity analysis aimed at understanding radiative cloud and aerosol interactions, some of the biggest uncertainties in terms of understanding climate change, and just how large the magnitude that we project for the coming decades will be is related to that, as well as the human choices. How much are we going to continue to use fossil fuels? How much are we going to emit into the atmosphere? How is population going to increase? How is economics going to develop worldwide, et cetera, which all affects scenario development. But on top of that is the uncertainty in the model that we're then trying to reduce as well. So why blue water? Blue waters. The science being done in this project couldn't be possible without using blue waters. The dynamical cores in CSM enabled the high resolution studies. and that requires the Petascale machine. The high resolution regional climate studies are also possible because of blue waters. And then the super ensemble approach used in the climate sensitivity studies also need Petascale. The next generation machines will allow us to go even further, because then we can go even better, even higher resolution yet, and look even further at local scale phenomena and changes in the Earth climate system and what that means to humans at the even further at the local scale. What I'm going to do today is just give you some examples of the kind of things that we're seeing. So with CESM, looking at these, using this kind of snapshot approach of looking at a few decades at a time rather than the continuous runs that we're also trying to do now. We looked at two different time periods. The present time period, when CO2 levels have varied from about 360 parts per million to today is actually closer to 400 parts per million. And a future time period, assuming that we, in this scenario, that assumes that we continue to heavily use fossil fuels, that results in an increase in CO2 of about 800 parts per million. And in that case, focusing in on the oceans here, because we're going to focus in on tropical storms, we find a significant increase in ocean temperatures projected. We've already seen a significant increase, about a little, roughly at 1.5 degrees Fahrenheit, 0.75 degrees centigrade over the last century. We expect a much larger increase over this century if we continue the way we were going in terms of emissions and what that means to the climate system. And those warmer temperatures in the oceans are likely to lead to some interesting effects on tropical storms. So the analysis that was done, at a 1/4 degree resolution, you can actually see a hurricane form and evolve in these models and follow it across the world. If you want to, we have movies showing that, but I'm not going to show you that today. What we did find is that if you look at the past time period and the future time period, and then look at the, first of all, looking at the past time period, and then what does the model represent the kind of observed climatology for these hurricanes and tropical storms? And the answer is yes, it looks quite realistic. But then when we look at the future time period, we find that overall, there's a significant decrease in the number of such hurricanes in certain parts of the world, and in this case, particularly in focusing on the North Atlantic. If we look at only at very high intensity hurricanes, though, we find an actual increase in the number. So other studies have suggested that's the kind of pattern that should occur, but this is one of the first times we've really been able to show with a very high resolution model that really is that what really would be expected. Likewise, we find that you get about a 20% increase in precipitation in the future events. This compares both for small tropical storms versus the larger scale ones. In both cases, the models calculated an increase in total storm precipitation. Overall, globally, we're finding that when it precipitates, that you get more precipitation in general. That's both an observed phenomena and is also being seen in the models. In fact, the current models tend to underpredict how much changes have actually occurred, but we expect that to also be the case of these very large tropical storms.
Is that only during storms?
I'm sorry?
Is that increase in precipitation only during storms?
Any
precipitation.
Yeah, we're more likely to see large precipitation events in general than in the past. So if you took at say the top 1% of the amount of storms in the northeast U.S., there's been an increase of about 70%, in the Midwest about 40%, less so here in the West, but still in the positive side. One of the other aspects of this analysis is shows that the importance of particles, and to show that particles actually contribute significantly. So the fact that humans emit various gases and particles directly into the atmosphere that then, the gases form particles, such as sulfur dioxide, for example, forming sulfuric acid particles, and emissions of soot and other things we put in the atmosphere can have an effect on the hurricane formation. Previous version of the model had been a bulk aerosol approach, which just accounts for mass. The new version, which we were able to run on Blue Waters, includes a model approach to treating particles, and that does generally appear to giving much more accurate results compared to observations. I mentioned earlier that we're running these long-term runs going from 1850 to the current time period and then beyond. And those runs are still ongoing, but we think that that's going to be really important for helping us to better understand at the global scale, not only things like hurricanes, but other types of storms and other severe events in ways that couldn't be done previously. With the WRF model, we're looking at regional scale analysis over the US. This is a project being done by one of my graduate students. And with that model, we're looking at 12-kilometer resolution, so about twice the resolution of the global model, using a global model as the boundary conditions and then looking at the US in finer detail. And we find we get a much better representation of precipitation, for example, with the regional model at that resolution compared to the global model, which was a 1-degree resolution, 100-kilometer resolution. And in this way, also able to look at, again, severe weather events and what they mean in certain parts of the US. This study is being done for the Department of Defense towards looking at how climate change can affect different military bases across the US. But it has many other applications towards looking at impacts of the changes in climate on our society throughout the country. So right now we've already run the model with the NCAR, a little bit older version of the NCAR model called CCSM. The new version is called CESM, and we're in the process of completing analyses with the GFDL model. Global model is boundary conditions, and we're just about to start, if it hasn't been probably already started this week, running the UK Hadley Center model. Also as boundary conditions. So that's going to give us 3 models to compare the resulting effects of fine resolution analysis over the US and be able to compare with each other and to see what differences those global models make on the boundary, in terms of the boundary condition effects on what's going on in the US, to do a much better job of looking at these details and the differences between models and how that affects resulting impacts. Finally, if I look at the, we're also using a version of the WRF model called CWRF, the climate version of the WRF model that Xinzhong Liang, who's now at the University of Maryland and had been at Illinois, has developed. And first of all, he did a series of analyses to look at, and I'll go ahead here a little bit, looking at radiative processes, cloud processes, and aerosol processes, where you have many different, you have a large range of uncertainties in these treatments of these processes. And the question is, could we maximize or optimize the treatment of those processes relative to each other in terms of getting the best possible representation of the past climate, and then see what does that mean to the future. And so those analyses are ongoing. The 25 ensemble members have been developed, and we're in the process of running those right now on Blue Waters. And from that, try to do a similar thing with the global model to see what really ends up being the most optimal choice. When we look at summer biases, for example, in temperature, the upper left-hand side shows the observations, and then a whole series of model runs different for these different ensemble sets. So were chosen to be optimal in the first place, but they, you see, in fact, that even for summer temperatures, they give large differences in terms of the change in temperature calculated. And so we were able to then fine-tune to look for the most optimal choice, and then do a similar kind of thing with precipitation relative to the observations to, again, so you want to do this with a whole series of different variables towards trying to understand how well are we representing climate processes, and if we find an optimal set, what does that say about our understanding of the radiation, cloud, and aerosol processes. There's one paper that has come out recently, which is the analysis of the tropical cyclones that I've shown, or at least part of it. Some of it was even, what I showed was even new beyond that paper. And that's in press right now. The 1850 to 2100 runs, as I mentioned, are ongoing. We expect that to really have a very significant impact, because no one else has been able to run at that higher resolution yet. GFDL is running at about a half a degree. We're running at a quarter degree. And the plans are in the future that will go beyond a quarter degree, probably to an eighth of a degree next. The WRF studies are well underway and are likely to produce at least a couple papers this summer. My student is going to spend the summer mostly at Argonne to work with them on completing those studies. And as I mentioned, the CWRF studies looking at the sensitivity analysis are also ongoing. Both those and the WRF studies are likely to result in PhD theses over the next several years, next 2 years. And all outputs are in our studies are expected to be available to other researchers. That's been part of the plan all along. We do want to give a special thanks to Ryan Mokos and other Blue Water team members for the help with a variety of issues over the last year. We've had a significant issues with the convection that I mentioned earlier, and it took us a long time to get over that, and part of it was caught up in how we're using the machine, but part of it was just going to the very high resolution created issues with the parameterizations that needed to be resolved. So I thank you. Yes.
So how do you account for sea surface temperatures in the future, especially for the lakes, Great Lakes?
For the Great Lakes? Yes. Okay, well, Great Lakes aren't sea surface temperature. So the model will derive its own sea surface temperature. Is a fully, the run we're doing for 1850 to 2100 is fully interactive. So it has fully interactive ocean, biosphere and land surface changes, and atmosphere. So the model will calculate those based on internal treatment. So there's a land surface model, for example, that would help with the treatment of land hydrology, including the Great Lakes, whereas the oceans is determined entirely from ocean modeling.
Any other questions?
Is there any limit to the resolution you would like to run at?
Yes, pretty much. Yeah, it's probably no, but yeah, but I think what we really would like to do is get the models down to cloud resolving. So for that, we need to be down to 1 to 2 kilometer resolution. That's not going to happen anytime soon, except in very limited areas. And that is, there are tests going over limited areas right now. We would like to get that at the regional scale, probably in the next 4 or 5 years. But that really would depend on the next thing beyond blue waters to be able to go there.
Final question? I have one there.
How do you use your research to impact the insanity of climate deniers? How can you move the political spectrum?
Well, it's a very good question. um, I'll announce it here. I got asked 2 weeks ago, or 2.5 weeks ago, by John Holdren to join him at Office of Science and Technology Policy within the White House to be the expert on climate change for the government, and I will be dealing with that. Communication is important. I'm not sure there's anything can be done with this Congress, though, because as they've outright said, no matter what President Obama does, they're going to oppose it.
Well, and they're not scientists.
And they're not, yeah, they'll say they're not scientists, but they certainly could say they know a few. And if they want to come to me, I'll help them anytime they wish. But so it's a little bit beyond what I can do. All I can try to do is be the best educator, best communicator I can be, and try to help get others to also help me do that. And we'll be working on that.
Okay.
Thank you.
Thank you.